Hello and welcome to MEM-15 Senior Design Team presentation for the final spring term. Our advisor is Dr. Yuri Gogotsi, Director of Drexel Nanomaterials Institute, DNI, and the 2D Materials Spray Coater project is also sponsored by Dr. Gogotsi. Our mentors, Dr. Narendra Kura, Mark Anai, and Adam Goad, are also part of the DNI team. My name is Bulan Sajin. I am the project team manager. Soon you will also hear from each of my teammates. Brian Brenninger is our lead mechanical design engineer. Grayson Calatel, lead controls engineer. And Solomon Jose, lead software engineer. Although in our project we were primarily working with MXenes, which are two-dimensional materials made from the carbides and nitrides, incorporated from transition metals like titanium, our system can provide solutions to many other water-soluble 2D materials. An airbrush, hairdryer, and a small glass substrate, about 1 inch by 1 inch, taped on a metal base. We're looking at a snapshot of a very time-consuming manual process. In this next video you're about to see, we would like to highlight the most time-consuming part of the process, which does not require a lot of skill sets. As you see, there are two critical steps in the process. The first one is depositing MXene on the entire surface. Then, using a hairdryer to remove the moisture from the surface. This is done in order to allow MXene flakes to settle on the substrate surface properly so the next layer can be applied. The key to this process is achieving maximum uniformity to increase conductivity.
Our project is immediately targeted for the research community in Drexel Nanomaterials Institute. On a broader sense, our device can benefit any researcher looking for an automated system to spray coat with 2D nanomaterials. We have broken down the stakeholder needs into 5 different categories. In terms of spatial requirement, the device should fit inside a box of about 28 by 61 by 39 inches. Substrate area should be a minimum of a foot squared. In terms of maintenance, the airbrush should be detachable for quick cleaning, and there should be valves to switch between the spraying solutions. In structural requirements, our device should be able to contain at least 200 milliliters of spray painting solution. Height and tilt of head mount should be adjustable. Controls-wise, the user should be able to alter variables such as spray speed, spray pattern. Adjustable air pressure up to 135 psi should also be available to handle viscous solutions. Finally, quality-wise, the spray-painted substrate should have a uniform film thickness up to 20 micrometer and a minimum conductivity value of 5,000 Siemens per centimeter squared. In order to solve the problem at hand while meeting the stakeholder requirements, we decided to automate the current process using computer numeric control technology and related tools. This solution was attractive because it is time-tested and being widely used in the industry for a variety of applications like CNC milling, 3D printing. The established tools based on this technology, like the G-code system, open-source CNC controllers, and softwares, enable the team to start designing from the get-go without the need to reinvent the wheel. A custom graphical user interface was developed by the team to generate G-code. This GUI served as a bridge that enabled the team to use the standard CNC tools, such as those mentioned previously, to execute the spray coating tasks automatically.
Our project team's approach to the automated spray coating system consisted of creating a work breakdown structure. This allowed us to decompose the project into 5 high-level objectives. The first objective consisted of project management, which includes planning, meetings, and administrative work. The second objective consisted of operational requirements and includes stakeholder needs and verification and standard work documents. The third objective consists of the mechanical design and includes the XY gantry frame and head mount along with the lower level work packages. The fourth objective consists of the electrical system. This includes the controls and the user interface software along with the lower level work packages. Finally, the fifth objective consisted of the pneumatic system. This includes the process and control air as well as the lower level work packages for each.
The design consists of three major subsystems that control distinct attributes. The process air subsystem provides contaminant-free pressure-controlled dry air for pneumatic components that are critical for the coating process, such as solenoid valves. The linear motion gantry subsystem allows for accurate positioning of the spray gun and diffuser. Also, a bulk fluid supply frame has been built around it. The control subsystem provides pre-programmed processes for a variety of substrates of different shapes, sizes, and film thicknesses.
During the mechanical design phase, our team utilized two different 3D parametric modeling software packages to design the key features of the system. Both Autodesk Inventor and PTC Creo were used and files were shared by converting the files into a step file format. Software used for the controls and GUI consisted of Visual Studio using the C# programming along with CNC.js, which is a CNC interface to run the TinyG controller. Custom-made components were machined using a CNC mill at the Drexel machine shop, or they were 3D printed at an off-site location. All machine components were machined from 6061 aluminum because of its weight to strength ratio. 3D printed components were printed using a carbon fiber reinforced nylon, which additionally has the same strength as the aluminum.
In the following a few slides, we'll talk about the features of the system. The air compressor we have specified for the project is a 2 horsepower, 4-gallon portable compressor, which can generate up to 135 psi air. The air dryer is an 18 SCFM refrigerated dryer that can provide approximately 5 degrees Celsius pressure dew point, and it is rated for 150 psi operation conditions. Additionally, the two pre-filters provide protection from particles between 0.5 to 5 microns. And the three regulators, one for airbrush compressed air supply, one for airbrush trigger solenoid valve, and one for the air diffuser solenoid valve, allow pressure control for those individual components. Next, we review the fluid system, which has three 600 milliliter containers. The twist-off top containers have a built-in air vent that allows gravity feed to work smoothly. These bulk containers can be used for large-size spray coating requirements, as well as cleaning solution or water to flush the system from contaminants in order to keep the airbrush and tubing system clog-free. Each container has corrosion-resistant ball valves with 6 millimeter tube connections for easy push-to-connect type of access. Additionally, an aluminum frame assembly built around the entire gantry supports the fluid supply.
The XY gantry is an automated 2-axis platform with over 1 square foot of usable spray area. 3 precision ball screws are driven by 3 NEMA 23 stepper motors to allow for accurate positioning of the head mount. As seen from the photo on the left, the head mount holds both the airbrush and the air diffuser. The purpose of the air diffuser is to dry the substrate in between each spray coat layer. The photo on the right shows the trigger mechanism used to activate the airbrush. This consists of a small pneumatic cylinder and a linear slide system. Features of the head mount include a manual height adjustment range of 4.5 inches and a manual tilt mechanism that allows for a rotation of plus or minus 15 degrees. Both adjustments can be locked in place to reduce unnecessary vibration during machine operation. Based on the spray coat application, the user now has the option to mount two different size fluid reservoirs to the system. For smaller spray coating applications, a 7 milliliter or 15 milliliter reservoir can be mounted directly to the airbrush as shown in the picture to the left. For larger spray coating applications, an overhead fluid reservoir can be used and holds up to 600 milliliters of solution. This can be seen in the photo on the right. Finally, the head mount was designed to allow for easy removability of the airbrush. The user just simply removes the two socket head cap screws, which releases the clip and removes the airbrush. This allows for easy accessibility for cleaning and maintenance of the airbrush.
Team developed a C#-based custom GUI that can run on any Windows-based platform. The GUI helps the user to change the spray coating parameters such as number of cycles, speed, etc. The GUI can automatically generate a text file containing G-codes, which then can be uploaded to the device. A Windows-based software called CNCJS or a website called Chili Pepper can be used to do that. Even though Chili Pepper option is available, it is advised to use CNJS option inside the GUI. But the user will need to install CNCJS software prior to using that option. So as you can see here, this is the control interface of the GUI. So this is the welcome page that you'll be seeing after you open the .exe file. In this home page, you can see different buttons. The new project button takes you to the page where you can actually change the parameters for spray coating. Developer details button takes you to the page where you can actually see the contact info and details about the developers of the software and product. The home device button generates a G-code that can be used to move the head mount assembly towards the user. This helps the user to change the fluids and the angle of tilt, etc. of the device. The close button can close the GUI. This slide shows the different options available to the user. You can change the spray coating parameters using the drop-down menus or text boxes. You can access CNCJS using the CNCJS button. The info button on the bottom shows the user how to use this page. The user can save and import templates by clicking on the corresponding buttons. A G-code can be generated by the GUI after filling up the corresponding boxes and clicking the Generate G-code button. Current cycle G-codes can be used to clean the device. You can use Chili Pepper by clicking a corresponding browser and clicking the Access Website button. Or you can use the Access CNCJS button. The Access CNCJS opens the CNCJS software, and the text file containing the G-code can be sent to the microcontroller through there. The Close button closes the GUI forum, and the Home button takes you back to the home page. This slide shows how the G-codes and templates that are created by the GUI are stored in your PC. The text file shows the different G-codes you created, and the Excel format files are the templates.
Control interface of the device. After generating the G-code as a text file using the GUI we made, it is then uploaded into an open source software called CNCJS. This software is used to execute the G-code. This software also lets the user manually move the head mount, send desired G-code from console if needed, and do operations like homing. It gives the user a preview of the spray pattern. While the device is running, it also lets the user execute soft stop and then resume later. Our device is equipped with an emergency stop button so that the user can cut the power to the device in case of a failure. The device also has limit switches on each axis to prevent the head mount from crashing into mechanical boundaries of the gantry structure.
Couple of standards our system complies with worth mentioning. Air dryer complies with ISO standard that specifies contamination levels allowed. Additionally, the multi-axis motion control system, G-code-based programming language, which is designed for applications that require precise motion control, conforms with NIST. We estimated the overall cost will be reduced significantly over the years. This is largely due to automation and the calculations made based on anticipated hours of manual process performed during the entire year. Additionally, roughly 25% of less raw material usage expected, which will decrease any potential environmental impact. We also predict a positive social response, especially from the researchers' point of view, as they will be able to spend more time on their research rather than performing a tedious task. Additionally, we identified some ethical concerns regarding our system. It is directly related to the material properties of vaccines, such as its performance in electromagnetic interference shielding. We think our device can be used to manufacture superior EMI shielding enabled products faster, and that could be weaponized by some ill intentioned individuals.
In order to stay on task, a project plan was defined and implemented throughout the life of the project. The 5 major phases of the project were defined and scheduled and can be seen below in the project plan. These phases consisted of definition of scope, design and specifications, prototype build, test and redesign, and optimization. Prior to the start of the spring quarter, a complete system integration test was successfully performed. Data collected from this test was to be used for optimization. However, due to COVID-19, all optimization stopped. Future project teams will be able to use this data for further optimization of the system. For the automated spray coating project, the team was given a max budget of $7,000. All money spent was allocated to 5 major categories. These categories consisted of the gantry and head mount, the control system, the control air system, the fluid system, and miscellaneous hardware and fasteners. As you can see, the total amount spent was just under $3,700, which was well within the allotted budget.
Let me demonstrate the first test that we performed after prototyping the device. In this test, the device is attempting to spray coat linear strokes with Maxine. The prototype was a success and provided promising test results. Even though we cannot quantitatively measure the uniformity of the spray coat due to campus closure, our mentors who have extensive experience in spray coating did approve the quality of this spray coat as promising. Had the campus been not closed right after the first test, we would have implemented the corrections to few problems observed during the test. One of the main problems observed was that Chili Pepper software, which was used to send the G-code generated, malfunctioned sometimes and failed to execute the send G-code. To fix this problem, we replaced the Chili Pepper software with a similar one called CNCJS. With this change made to the control system, another test was performed to verify it. Since we did not have access to the gantry in the lab, we took the electrical box of the system to one of our teammates' house and connected it to a 3D printer to test the change made. As shown in the video, the problem was fixed.
Restrictions that came into place due to the COVID-19 situation was a tremendous setback to the team's goal. The team's initial plan was to hand over a functional prototype to DNI at the end of academic year. The team couldn't finish the optimization of the device due to COVID-19. The G-code generation algorithm and design had to be changed based on the trial run. The team split the workload based on the individual fields of expertise. I worked in the G-code generation algorithm and integrating CNGS into GUI. Grayson worked on modifying his home 3D printer to test the GUI at home. Bullen and Brian worked on developing a limit switch bound and virtual prototype. The team also was tasked in developing a user manual that the future team and the Department of Nanomaterials can use in the usage and repair of this device. By splitting the workload like this, the team managed to complete the device construction to a point that the next team can make the designs further without much trouble.
The team was able to successfully prototype a multidisciplinary solution starting from concept creation all the way to testing using project management tools. One of the most challenging aspects of the project was the creation of an intuitive graphical user interface. This is largely due to none of the team members had any past experience in software development tools using C++ or Visual Studio. For the future iterations, the next team who picks up our project from where we left, there are a few suggestions our team can make. Substrate holder that can serve as a bed to hold any access solutions. Introduction of a heated vacuum bed to increase testing capabilities under different conditions. Integrating multiple spray guns and multiple spray solutions to layer different 2D materials on top of each other. And the use of a robotic arm for three-dimensional spray coating, to list a few. And we thank you for watching our presentation.